Hey everyone, how's it going? Today I'm going to be showing you one of the most exciting parts, which is using AI for stock trading. We're going to be using neural networks, which are some of the most advanced AI models that mimic in many ways the structure of the brain and can be used for a lot of advanced tasks. Now, this isn't financial advice. All of the risk is your own, but through this process of using neural networks and training them for stock prediction, you're going to gain a good intuition of how neural networks work. So stay tuned, and first thing I want you to do is stop what you're doing. Whether you're on your phone, on your computer, stop what you're doing, and I want you to go to collab.research.google.com, or you can just Google Collab. This is the equivalent of a Google Docs, of a Word document, but for code, and where you can write all of your code that we're going to be writing today. And I promise you, it's going to be way simpler than it seems. So we're first going to start with a new notebook, just the same way that you would start a Google Doc. And we're going to rename this, to Stock Prediction with AI. And then in brackets, I'm going to write neural nets, which is the neural networks we're going to use. Now, if you're new to Python, I highly suggest checking out one of my other videos. You will need some basics of Python for this, but apart from that, it's going to be really interesting. This is a bit more advanced type of model, but it's going to be really interesting to learn. So we'll start off with a comment. As you know, comments are started with a hashtag, like on Twitter, and we write import necessary libraries. And a lot of data science and machine learning, we use packages that other people have created in order to get the most, because there's tons of really smart stuff out there. So we'll start off by importing Yahoo Finance. And you can do that by doing import Y Finance as YF. So that's how we import Yahoo Finance. Next, as you've seen in the next line, we're going to import pandas. Pandas, you can think of almost like an Excel sheet, but for Python. So we do import pandas as PD. This is where we're going to store all of our table data that we need when we're working with a lot of data for machine learning models. Next, and very similarly to pandas, we're going to import NumPy. Yeah, they all have funny names. Import NumPy as NP. And that is how you import it. It's very similar to pandas. It's what we use for data analysis. Next, we're going to import matplotlib as .pyplot as PLT. Now, what matplotlib is a plotting library, as the naming suggests. So we're going to use it to draw charts. Next, we're going to do from sklearn .preprocessing, import standard scalar, and make sure that you have the caps here. And this, as you can imagine, there's going to be a lot of pre-processing of data to get it in the right format that the AI models can use. So that's what we're going to use it for. And last but not least, every AI model has building blocks behind it. And so we're going to import these building blocks by doing from TensorFlow.keras.models. This is how we get those building blocks. Import sequential. So sequential, this is a sequential layer. It is a layer of a neural network. I have a whole nother video about an AI degree in less than 20 minutes. And I highly suggest you look at that to understand more how these neural networks work. But essentially, they have several neurons baked within them, and you teach them through a lot of repetition. So we're going to do here from TensorFlow.keras.layers, import dense. And this is a dense layer. And so we're going to use this in order to create a layer that has a lot of different neurons and connections. And we're going to be using this to train the model. Cool. Now that you've got all the imports out of the way, we're going to create a new coding cell. So I'm going to run this. It should run all smoothly. And in the next one, I'm going to do a new comment and say, download the stock data. So to do that, I do data. Oh, so it's complained here, and it means that I have to check that I've written everything correct here. So sklearn, pre-processing, standard scalar. Oh, I wrote scalar wrong, so it's with an E. If you rerun that, that should work properly. And we'll just wait to make sure it does, and it does. You see in the check mark. Now we're going to download the stock data. If you remember, we imported Yahoo Finance as YF. So we do YF.download, and we can download any stock, but I'm going to download Apple. And Apple is denoted by the stock symbol AAPL. So that will download the data for Apple, but under what time period, right? There's a lot of data for Apple and a lot of historic data. So we're going to do comma, period, equals. We're going to do quote marks, and we're going to write 2Y, so 2 years. And last, we're going to do reset underscore index, and this just makes sure that we have this in the right format. So if we want to see what this looks like, we can do print. We copy this data into here, and we do dot head, and then put these parentheses. So if we run this, there we go. We downloaded the data, and here you have the first 5 rows of the Apple stock data. You have the date, you have the, as you can see here, the closing price, the high price, the lowest price, the opening price, and the volume. So what we're interested in is the closing price, right? At the end of the day, what is the final price that the stock has? And given the high price, the low price, the opening price, and the volume, given the data that you have during the day, how can you estimate the closing price? And so what we're going to do here is we're going to create a new cell. I'm going to do a hashtag for a comment, and I'm going to write pre-process the date feature. So basically for machine learning models, we understand how these dates work, but machine learning models and AI models only understand raw numbers like these. So we have to convert these dates into raw numbers. And one easy way of doing that is, for example, we're going to here take the data, this data that we have here, and we're going to create a new field, and we do that by doing square brackets, and we do date underscore ordinal. Ordinal just means that it's a specific format that we can put the date so that it's a longer and pure number. It doesn't have these dashes. It's not this date format, but it says the amount of seconds. And that's the seconds since I believe it's January 1st of a date a long time ago. So basically it's a really easy way we can convert this date format into the amount of seconds since a specific date a long time ago. So we're going to do date, square brackets, data, square brackets, date. So that takes this date, and we want to instead make it into a number. So we do dot apply, we write lambda, we do d dash, oh, I put an extra colon here, d colon d dot to ordinal, as you do like this, and we'll run it to make sure we spell everything right. That should be good. And I can now print this by doing, for example, if I copy this and I paste this, you can see here it's now converted into full numbers. And I can see the whole table here if I do dot head like I did before. And here you see that new format of the date. This is the date here, this is the date here, and the difference between these, you see, for example, is of a single day. So I think this is actually converted into days instead of seconds. So it's the days since a specific date. I think it's January 1st of 1990 something. So just to keep that in mind. Next, we're going to add a new cell. And in this new cell is when we're going to actually prepare the features. And features you can think of as inputs into the AI model. So here we write prepare features and target. So to do this, we write features equals, and I told you that features are inputs. So we can actually pretty much just copy these. So I do square brackets and I paste these in because these are all of the inputs that we're going to feed it. I'm going to remove close because the closing price is what we're going to be predicting. And I'm going to add date ordinal here. So we add the date ordinal and we remove, actually I'll just replace the normal date with that. So now we put these into quote marks because it is a list. If you've seen my other Python video, we know that when we put stuff in square brackets, it's a list. And here I put these all in quotes. So there we go. Those are all of them. And as you've seen here in the auto suggest, we're going to do target equals, and we're going to write, and next what we're going to do is we're going to write X. X in AI always means inputs and Y always means outputs. So X is what you give the model, Y is what you get from the model. So we're going to do X equals data, and then we're going to do features. So basically what we're doing here is we're taking all of this info, but only these fields, meaning that we don't take the date and we don't take this close, which is basically the end price. And we're going to do Y equals data close. So this is what we're predicting for. What we're predicting for is at the end of the day, what is the price, right? So that is what we add here. And what I'm going to do next is, well, I'm going to run this to make sure it runs fine. And I'm going to add one new code block. And I'm going to write a hashtag and I write scale the features. And so one thing that you find is that when these AI models get all of the data, next thing what I'm going to do is I'm going to split it into training and testing data. So I'm going to write here split into training and testing data. So what is the difference? When we have a lot of data, what we like to do is something like the following. We take 80% of the information that we have to teach the model how to do the task, and we take 20% of the data that we have and we use it to test the model, because the 20% it hasn't seen before, we've shown it only the 80% before, and it makes it a fair test to see how the model is performing. And this is what is called a train testing split. So here we do, for example, split underscore index, which is where we're going to split, and we're going to write int length of x times 0.8. What does this all mean? What we're doing is we're taking 80% of the amount of data. So length of x gives you the amount of data. And sometimes this cannot be a whole number. This, when you multiply by 80%, might be 0.123. But what is 0.123 of a row of data? That doesn't exist. And so we use int to round it to the nearest amount. So if I take 80%, let's say we have 100 rows here. If I take 80%, that would be 80. And because it's already a round number, it doesn't round it and it just keeps it the same. Next, we're going to do x underscore train. And we're going to write y underscore train. And this is going to be our training data. The way that we get this is we do x dot iloc. This is how we grab the data. We write colon split underscore index. So here I think I wrote it like this. So I'm just going to copy paste it here. And so this basically gives all of the data up until the 80th percent. And so if I copy this and put it here, instead of x, here I'm going to write y, and it has the exact same effect. Now I'm going to copy this whole line. I'm going to paste it. And instead of training data, I'm going to write test. So I write x test, y test. And here, instead of doing the split index here, what I do is I put it right after the colon. And what this means is I want the part after the 80% instead of before the 80%. So this just means I want this part. And so if you put it before, it's the part before the 80%. If you put it after, it's the part after the 80%. So that's how you make a clean split. And if I run this, these I can print, and I can do print xtrain dot head. As you can see here, it's all the data here. If I do ytrain dot head, it's only the closing price, which is what we're predicting for. Cool. Now into some more technical pieces. First of all, before we give data to a model as inputs, we need to scale the features. And this means that we need to normalize them. This is because you're going to have some data that has really high values, really low values. And sometimes these are so spread apart that it can be hard for the model to properly learn the distribution of this data. So what we're going to do is we're going to normalize this data, and we're going to write scalar equals standard scalar. That is what we imported. And this basically normalizes our data so it's not as extreme, right? It just smoothens it out a little bit. So if we write xtrain underscore scaled equals scalar dot fit underscore transform x underscore train, what we do is we give it this x training data that we showed before. So this data, and we're going to normalize it. And I'm going to show you when I run this. If I now print it and I do dot head, it's not showing, and that's because it's in a different format. If I just show it like this, you see that now it's normalized. What it means is it picks a range which is smaller. And instead of this being like all above 0, or it's 147, 147.5, these numbers are so close to each other, it can be hard for the model to learn. Here, instead, it normalizes it so they're all within a specific range. And this allows you more easily to be able to show the model exactly the types of differences that you want. Because in real life, some data will be really close together and some will be far apart. You want the model to just learn the patterns. You don't want it to necessarily learn the exact absolute values. And I'll show you in a second why this still works. So if we do x train scaled, that is that data scaled. If we do x test scaled, so we can copy all of this line, and instead of training, we write test. So instead of training, we write test. Instead of training, we write test here. So if we run this, that works all well. And now we're going to get into the really juicy part. And the juicy part is actually creating this machine learning model through neural networks. So we're going to create here neural network, and you're creating it pretty much from scratch using those building blocks that I told you before. So I write model equals sequential. So this is how you create a sequential model, is how you create these stacks of layers of these building blocks that are going to be used. And the building blocks that we're going to use, here I'm just going to go here and do a tab, are called dense layers. These are layers with neurons within them. So every time you write dense, it's creating one layer of, let's say, in the brain of this machine learning model, and we're going to add neurons to this layer. The way a neural network works is that you have multiple layers stacked on each other, and each one is learning something about the inputs you're given and passing those inputs, processing them, and then the outputs are then passed on to another layer. So you have these multiple layers of intelligence that are learning. So here, let's say that I want to create a layer with one neuron. I can write 1. If I want 2, I write 2. If I want 4 neurons in this layer, I write 4. I'm going to write 64. And that's going to be the start of this single layer. Next, we're going to create, this is more advanced, but we're going to write what activation function we want. This basically is, I wrote activation, right? This is basically what is used to process the output number that this layer gives. It gives an input, and how are you going to smoothen the output at the end? So we're going to write relu. Relu is a type of activation function. And now it has no idea what I'm sending it, right? So I have to tell it what shape. What shape should I expect, right, is a model. I write input shape, and I write x underscore train underscore scaled dot shape, and I do 1 and then comma. And that is the shape that we're going to give it. We're basically taking the shape of the scaled weights and the first, in the second column here. So that is basically already, this already starts to form our network of neurons. And if I want to create a second layer, I can very easily copy paste this. So I can do a comma here, and I'm going to paste this, make sure this is properly aligned. I'm going to now do 32 neurons instead of 64, and you don't have to say this input shape because it knows from the previous step. So now I'm going to do comma, and lastly I'm going to do a dense layer, and I'm only going to add 1 neuron, and this 1 neuron is going to help us because it is the output layer. So this output layer is going to give us the final single answer. So if I now do model.compile, and this is how we compile the model. And you can also select an optimizer. You don't have to, this is more advanced, and I can cover this in another video, but I'm gonna write Atom because I like the name Atom, and it's also a good optimizer. And the loss is MSE. This is mean squared error. This is what the model is optimizing for. Basically what happens is the model runs, it gets given our training data, right? This is what it uses to learn. And we've given it so it can study. And what it's going to do is it's trying to predict from this data that we give it in the training data. It's going to, given this data, try to predict the closing price. But every few steps that it does, it's going to measure how wrong it was and correct itself. The way that it does that is through the error function that we write here, which is mean squared error. So it takes the error, let's say it predicts the stock price is 200 and the actual stock price is 100, right? What is the difference between 200 and 100? It's a difference of $100 wrong, right? It predicted 200, the actual answer was 100, so it was off by 100. What mean squared error does is it takes the square of that error, and the error was 100, so the square root is 10,000, right? So 100 times 100. So that is what mean squared error is. The reason it is that way is because if it's wrong in the positive sense or it's wrong in the negative sense, the square just helps combat that. So you ensure that if it's too high and if it's too low, it'll have the same impact in order to regulate it. So that is what mean squared error is. And I'm happy to cover both of these more advanced parts in another video. And now that we've compiled this model, we've put this together, we now have to train the model. And we do that with model.fit. And as I told you, we're going to use the xtrain underscore scaled. So xtrain scaled, this is our scaled training data here. I'm going to give it the answers of the training data, but I'm not going to give it the answers from the test data. This is the secret stuff. This is the final exam. I'm going to write epochs. This is the amount of runs that it does when it's learning. So I'm going to say 50 runs of learning. And batch size is how much data it's processing at one go. So I'm going to say 32, batch size 32, so 32 in your batch each time, and verbose is 0. So it's going to keep quiet. I'm now going to run this, and it's giving us an error. Let's just make sure that we have everything right here. I know what I did wrong. Here, I'm supposed to give a list. So I'm going to do square brackets here, and I'm going to do another square bracket down here. And this should solve it. As you've seen, it's a list because we have comma separated values. So I'm going to run this, and now it's another error. So it says optimizer. It doesn't know what it is. So I think it might be the American spelling. So I'm going to put a Z here. And there we go. It's created this machine learning model for us. Now, lastly, what we're going to do is we're going to start to predict, right? So given that it's been training on this training data, what is it going to do when we predict on this test data? So if we do y_pred equals model.predict, and then we do x_test scaled dot flatten. So if I run this, it'll give us the predictions, and I can even print these predictions to see what they look like. So here are all the predictions of the closing prices, and basically what it's done is it's taken all of the features, all of this data of high, low, open, the date ordinal from the test set and predicted on them. And this is the predictions of the model. And now we're going to compare it to the actual prices. So the way that we do that is very simple, is here we're going to write actual_change. So what is the actual change that happened is y_test.diff. So this gives the difference, right? And I do .iloc 1 colon. So this will give us, basically what I'm doing here is I'm taking the difference between yesterday's price and today's price. And basically that tells me, has the stock gone up or down in that given day, right? So next I'm going to do the predicted change, which is, this is what the model thinks is changed, like has it gone up or down? And I'm going to write pd.series ypred, index equals ytest.index dot diff at the end here, and then we do .iloc 1 colon. So this is just a fancier way of being able to say what is the difference between yesterday and today out of my predictions. These are all the predictions that I did here, right? This is the differences day by day in stock price for the actual data. Here's what it's predicted day by day is the change. So now we want to see what is the accuracy, right? So we're going to say the directional accuracy. So the reason I'm saying directional is I'm seeing here, okay, can the model predict whether it's going up or down tomorrow correctly, right? Obviously, it matters how much a stock price goes up tomorrow and how much it goes down. But just very simply for this tutorial, does it know, how accurate is it of knowing whether it's going up or down correctly? So I'm going to do np.sign, and I'm going to do actual_change. So this is the sign of this change, because the change can be negative, it can be positive, right? And so we're just checking, is the change the sign of the actual change? And I'm going to copy this. The same as the predicted change. So basically, are they both negative or are they both positive, right? And then we're going to do dot mean, basically because this is taking all of the differences in signs. And then we're going to do times 100 because that is the percentage. So last thing we're going to do is just print. And then here it's basically saying everything, but I'm going to write F to format this. And I'm going to say directional accuracy is, and then I'm going to do curly braces. I'm going to post this into here, and I'm going to write a percentage sign. So this is how accurate it is on a direction basis. Here I've written something wrong, so I'm just going to double check. Here it is. I think I have to do predicted change dot values. And here I also have to do actual change dot values. Cool. So here we go. I'm going to actually remove this line. I'm going to run this, and it says the directional accuracy is 49.61. So that's not very good, actually, because it means that it is wrong. So it's a 50% chance that it's correct. Right now it's 49%. But what you can do, for example, is if I run all of these steps again, I did runtime run all, you're going to see that this directional accuracy might change slightly. And so if I run these again, it's 49.8. If I run it one more time, or if I train it even more, it's 49.83. So what I can do, for example, is go into here and I can increase the size of these activation layers. So if I do 128, for example, and then here I remove this part, I can run a slightly bigger model. And it's 49.94, so maybe it's improved slightly, but it's hard to tell. I can add even more layers. And so here I do 128, and here I do something like 256. So I can run this. Now it's 50.38. Maybe that's a bit random, but basically the size of this model will somewhat affect the amount of pattern recognition that it can inherit. So if I put this here and let's say that I try 512, here it's giving 50.6, and that's slightly better than average, right? If someone guesses it's 50%, here you're 0.6% sometimes in this test environment correct. So that starts to be kind of interesting. If I now, lastly, I'm going to put plot. So I want to plot this data. What does it look like? So I do plt.figure, and here I do fig size equals 12,6. So I'm going to create this canvas, which is 12 by 6. I'm going to do plt.plot y_test.values. Label is actual prices, and marker equals O. And I'm going to copy this. So this is the test values. And now I'm going to change this to pred values. So it's like predicted prices. And the marker is an X, so we can tell the difference. And lastly, what I'm going to do is plot plt.x. Label is the date, as it says here. Whoop. And here I put y label is the price. And I'm going to then do plt.legend because I am a legend. And we're going to do plt.show to show it. So here, if I run this, it's going to create the plot. I might have to remove here the dot values. But if I do that, here we get a plot of what it's doing. So here are the actual prices, and here are the predicted prices in orange. As you can see, this model still hasn't learned much, right? It has a lot to learn. It's been able to get right now a 50.6% chance likelihood of knowing from today what tomorrow's price might be, which is a little bit better than random, but you can pretty much assume right now is no better than random. But it's learned at least that the distribution sometimes of going up and down is all right. Now as you can see, there's a lot bigger error because this chart of actual prices doesn't coincide with the predicted prices. One thing that can happen is that previously it may have learned that the price was around here. And so it's basing this off historic data. But one thing that you can understand and do a little bit better is as you go scaling this model and making it bigger and bigger. So let's, for example, copy this and instead here write 512 and here write 1024. If we rerun this, you can start to experiment and see how does it change when I add more neurons to the layers of this model. What happens if I play around with them and change them? How does it affect directional accuracy? And note that this is one specific sample. You want to test on as much population data as possible to get even more accurate. Here we've seen it's jumped to be a little bit more accurate, and but by very little, right? So you can start to see how does this scale as I make a bigger and bigger model. So that's been it for this tutorial. I do highly recommend that you play around with this. As you can see, I'm having quite a bit of fun here just playing around with these numbers and seeing how it scales as you go adding more data. But I highly encourage you to test this yourself and see how accurate you can get this. And please don't take this as financial advice. This is machine learning and AI knowledge. I do very much hope that you heavily consider and understand better how these algorithms work, how the stock market works. And what I prompt you, if you have more time, is play around with these sequential layers. There's optimizers here that we haven't spoken about, loss, epochs here, which is the amount of runs that you do, the batch size. There's a lot of, these are called hyperparameters you can play around with and test more. So I highly suggest that you do that. Here we've gotten a little bit better, for example. And one cool thing you can do in Google Colab is you can change the runtime. It's running on CPU. I suggest that you use, I have the paid version, but you can use some of these other GPUs to train this even faster. And so what it does is if I do a very big model, it'll be able to do that a lot better. So for example, if I do, let me just do 2 to the power of 32, 2 to the power of 20 is this, but if I do to 15 is 32768. So if I do 32768, which is very big, and we do this divided by 48192. So now, because I've changed the runtime, I have to run these all, but basically it's going to run a lot faster on GPU. So you can see how this starts to change, and have fun with this, test it out, and let me know what you see. Drop on the comments if you have any questions, and hope you found this interesting. Please let me know what you'd like to see next, and hope you have a great rest of the day. Now, before we jump off, let's see if we can get this trained and we can see what the results are. So here we've gotten 0.6, which is slightly better than before. Here we see that it's not exactly still learning, but please try it out and let me know how you get on with it. Thanks a lot. Have a good rest of the day.